Today we're going to look at bivariate data. Bivariate data means that we have two variables instead of one. Bivariate, like a bicycle, has two wheels. So let's jump right in. We have two different temperature recordings, a low and a high, for a few days here. So we'll pause right now. I need you to put the low temperature, the X value, in list 1 of your calculator, and then the high temperature, the Y value, in list 2. I'm going to get my calculator on, and you're going to do stat and edit to get that information in there. Also, while we are paused, you need to create a scatter plot. Okay? So what we're going to do is have our low temperature be our X value, and the high temperature be our Y value. Our temperatures have to go, we start not at 0 is what I wanted to say. We start with both temperatures not near 0. So we're going to do a double lightning bolt, one for the X temperatures and one for the Y temperatures. And just like earlier this week, that's not the case when you get to science class. They have you start right in the corner. I'm not going to have you do that in math. We treat it differently. So for my X temperatures, I'm starting at 25, and I am counting by 2s. But you can't see my middle number because my marker is too wide to do that on this on the piece of paper. And then going up for our high temperatures, I'm starting here at 48, and again I'm counting by 2s. Once you have that drawn in, pause the movie and put the data into your calculators, list 1 and list 2, and plot those points on their scatter plot. See you in a minute. Real quickly on your calculators, stat and edit, and you should have data in list 1 and list 2. You can ignore my list 3 for right now, please. And just flipping back quickly, here's what your scatter plot should look like mostly. If you're slightly off, then that's okay. But just comparing the two, mine to yours. So in part B, we're supposed to use our calculator and find the equation for the line of best fit. So we want an equation of a line. So in your mind, you're thinking y equals mx plus b. But we're going to use our calculator to do that. So we've got our data in. We're going to stat, sliding over to calc. We need a line. So choice 4 gets us our line. We have to tell the calculator, list 1. So to do that, look at the key press. Second and the number 1, comma is its own button, and then second and the number 2. When you push enter, you should have some information. If you don't have this R value, we're going to need that in just a minute. So I'm going to go real quick and show you or tell you how to get your calculator to have the R value. If you don't need this, just skip this part. So to get that R value showing, we need to turn our diagnostics on. So I'll clear my key press history. Second and catalog. Notice that you are in alpha mode here. So we're going to find D for diagnostic. Once we're in the D's, you go down until you get to diagnostic on. So 7 times down, push enter and enter. Then when you do stat, over to calc, line reg, list 1, comma, list 2, that R value will appear. Okay, so back to our problem. We're supposed to use our calculator to find the equation for the line of best fit. Round to the nearest tenth. So our slope is our A value, and our y-intercept is our B value. So we have, rounding up our A value to 1.2 and our B value to 19.1. That will be our line of best fit. Letter C, using our line up here, what if we had a low temperature of 40 degrees? Low temperature is our X value. So in our equation, we are replacing the X with the 40. And you can plunk that right into your calculator. So that would be a high of 67.1 degrees. Moving on to letter D. 10 temperatures recorded in the month of May. They had a linear correlation coefficient. Whoa, that's old news. We've been there. It's just the R value. Okay? So their R value was 0.89. Up above, we have the information for the month of April. We have to go back and look at our calculators. What was our R value for April? About 95. So, did April or May have a stronger correlation coefficient? And April was stronger because its R was 0.95. To the back of our notes. When we talk about or compare two variables, we can talk about a strong relationship, which is what we saw on the front, the correlation. We can also talk about something called a causal relation. That's not casual, okay? That's causal. In other words, does one variable actually cause the other? So we're going to look at some examples of this on the back. In number 2, you're going to be given some information comparing two variables. Decide if the relationship is causal. In other words, does one variable cause the other? Okay, so the high temperature in New York City and the number of bottles of water sold. Yes, it's causal. The high temp will increase the water sold. Probably it also increases the ice cream sold, but that's not what this question's asking. In letter B, does a person's height cause their shoe size? Yes, that is also causal. Your body is in proportion. Imagine if you were really short or really tall and your feet were really small, you'd probably tip over a lot. Letter C. Does the amount that a person loses in weight, is that caused by the number of hours the person spends in the gym? Well, as long as you're actually working in the gym, then yes, your weight loss should be reflective of how long you're working in there. And then our last example. The years of education a person achieves and the salary. So how long you're in school and how much money you make. Take a minute and write down if you think that is a causal relationship. In other words, does the years that you're in school cause you to have a higher salary? And the answer is yes. It is possible to have a strong correlation but no causal relationship. Sometimes there is another variable that could play a role there. In our last example, we have the number of fires that were recorded and the damage done in dollars. So I'm going to ask you to go again to your calculator and enter your data into list 3 and list 4. So pause the movie while you get your data entered, and when you're ready, we'll come back. Okay, so we have our data in list 3 and 4. And so we're going to calculate, they want us to find the correlation coefficient, or the R value. So we're going to go to Stat, slide over to Calc. We need that line reg again, because we need that R value. But this time, be sure you're doing L3, comma, L4. And go ahead and look at the key press history. Second and the number 3, second and the number 4. Push enter, and we need that R value. And I'm thinking there's something wrong with my R value. I'm going to go with my notes, not with my calculator. So if you disagree with my calculator, that's great. In my notes, I have a correlation coefficient of 0.998, 7067928. We're rounding to the nearest hundredth, so that's a correlation of 0.99. So is this a strong or weak correlation? It is definitely a strong correlation. Does the number of firefighters, that's our X value, cause the damage done to the house? And the answer, I'm pretty sure, is no. Bryce and Tyler, I know you guys have some experience with fires. Maybe there's other of you as well as firefighters. The number of firefighters does not determine the damage to the house. How strong the fire is, or how powerful it is, that's what's going to determine the damage. Okay, so bivariate data is two types of data. We're going to use scatter plots to work with those, and we'll spend Thursday and Friday doing scatter plots. You're going to use your calculators a lot, so be sure you're pretty comfortable with that, and I'll see you tomorrow.